Hello, hello. This is the last installment, and now we'll focus on chapter 19. One thing I forgot to mention about the phenomena of interference, double slit, or even diffraction. There is a very nice website that is, there are many websites for simulation, but if there are some of you that are still not visualizing, have a hard time understanding these things that we are saying, still there is, you should Google it, but there is a nice website called phet.colorado.edu, okay? So they're called PHET simulations or PHET simulations. Okay, it's this URL you're seeing here at the top. So there are many for physics. And here is, for example, you have two lasers and they produce waves. And just like water waves, etc., we know it works like a double slit experiment. I know there's no slit here, but it works the same way. You see how there are positions where the light will combine constructively and positions where it will combine destructively. So you combine destructively, you see kind of there are rays here, sort of that's where destruction is. This is a screen and you have the maxima, and the destructive is where you get the black, the minima. Okay, there's a lot of little things you can play. You can play with the separation and see what different things will happen, how the pattern will change. By the way, the same thing could happen with, although we are focusing on light waves, this could happen with sound waves, right? The phenomenon of diffraction can happen with sound waves. Say if I want to see a graph, you can even see a graph of what is going on. And anyway, so you can see the particles of the sound actually vibrating and forming regions of maximum constructive and destructive minima sort of in the middle. Still happens. The phenomenon of diffraction, you can look at what happens when you send a laser beam through a little square or a circle, a square, multi-slit. So you get, that's the diffraction when light really spreads out, Okay. So PHET simulations, anyway, just some basic things about waves is a nice one to practice, to play. If you're still having trouble visualizing things, maybe this will help you. And you find the connections to everything we've been trying to show you in the problems and in the lab as well. All right, so chapter 19, now we go away from wave optics and we talk about ray optics. Is also a topic of physics called geometric optics, okay? So this is also called geometric optics. What is the difference between wave optics and geometric optics? In wave optics, we need to remember that they are waves, that they can combine, superpose, and there will be constructive and destructive interference, right? Superpose, destroy, or combine with each other positively. Now, in geometric optics, we're going to imagine that instead of light being a wave, we're going to connect all these waves. So say here we have a wave, right? Or lots of wave fronts like this, and we're going to connect them all with a ray. So we're going to call this as a ray of light. So what is this ray of light? Is basically the connection of all the wave fronts, okay? So it makes 90 degrees with sort of the wave fronts here. And so when you connect all the wave fronts, that's a ray of light. So it's going to be a straight line. And when you have straight lines, you can start making triangles and creating doing some trigonometry. And so is geometric optics, because we're basically going to use a lot more trigonometry than once we just focus on what the rays of light are doing. All right, so we'll skip this section 19.4, okay? And we are briefly going to mention, well, the color and dispersion, what they are, how they, what happens on our everyday life, and etc. This I will leave for Thursday, okay? And this is what we're going to see today, including in the refractions. Yeah, that's it. This is what we're going to see today. These are the equations. There aren't that many. This table here, however, is a big table for conventions of signs. So it's not a difficult topic. It's just that if you're given a table that's like a cheat sheet where you follow the convention, we're going to learn how to do that. You do fine. So all this part here, okay, all this part here, including the convention, etc., 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 we're going to cover on Thursday. It has to do with image formation and all. This is essentially what we're going to do now, okay? So we end up in total internal reflection, short for TIR. So let's go over this. So the ray model of light, as I said, we're just going to connect lots of wavefronts of light and call that a ray. So stop talking about the wavefronts and the wave aspect of it and just talk about where it's going. So light rays are straight lines. The light rays can cross. A light ray can go forever unless it interacts with the matter and an object is a source of light rays. Objects may be self-luminous, like the sun, like a light bulb, or maybe reflective, like our own bodies. Our eyes see by focusing a bundle of rays. So let's for sure examine some pictures, like for instance this one here. If I have the size of a tree here, a tree doesn't shine. I mean, that's just if it's a Christmas tree full of light, but let's say there was light from the sun there is reflected on the tree, and then that passes through, enters a little hole. There's a little hole, could be your eye. This hole could be your eye. But there's a box here, and there's a little hole, could be the eye or a camera, right? And so the light from the top of the tree always follows straight lines. So imagine straight lines that will enter the hole. There's a straight line that enters the hole and ends up right here projected on the back. If this was the eye, on the back of your retina. If this is a photographic camera, in the back of a CCD camera or something, right? The digital camera. The bottom of the tree goes along a straight line. Choose the straight line that actually passes through the hole, and you're going to see it like that. So every time an object passes through a very small orifice, a very small opening, it's going to be projected upside down. So that happens with our eyes projected on the retina in our eyes is all upside down world, all the upside down image. And then our optical nerve in our brain does the miracle of making sense to us of the whole world, right? But yeah, photographs. So for instance, even if you're going to say play slides in the old movie theaters when they had movies, films that they had to put in a slide projector, right? They always had to put the movie upside down because when it passes through the lens of the projector to project on the huge movie theater screen, unless they made the movie upside down, the film upside down to be projected, it was going to be projected upside down on the screen of the movie theater. Now, what if you have a point light source? So this is a point source, okay? This was not a point source. This was an extended source. Now, if you have a point source passing through an orifice or passing through any kind of filter frame here, it will always spread out. It spreads out. It goes in all directions. Light will go in all directions, and we only are interested in the rays that go through those sort of slit screens, and it just gets bigger and bigger as it spreads out. So examine that, and then you'll be good. So we call HI the height of the image. So the image would be whatever is projected. HO is the height of the object. We call DI the distance between something, an optical instrument. So it could be just the hole, could be your eye, like the pupil of your eye with the crystalline lens that we have inside our eye. It could be the diaphragm of a photographic camera. So whatever is the opening here, so whatever is the optical instrument right here, that distance to the object is called DO, and that distance to the image is called DI. So it's shown here, DI is the optical instrument to the image, and DO is the optical instrument to the object, okay? So if you have just simple, no lens, no mirror, no curved mirrors here, just a simple hole, right? Okay, and we're not considering any more complicated effects now yet. Light is just a straight line entering that box with a hole. You're always going to have this proportionality analyzing these triangles, that AGI is to AGO, just like DI is to DO. So a few questions for you guys to look at on your own. Here is a problem we're going to solve together. It's very simple on the at the beginning, just understanding straight rays of light, okay? So a 5 foot tall girl stands on level ground. The sun is 25 degrees above the horizon, okay? So so how long is her shadow? Okay, guys. So her shadow is going to be this long here. It was going to be X, basically is asking X. So this drawing that you see right here was not in the book. It's not in the book. It's a drawing that, you know, we get the instructor solution manual. You don't get this drawing. So you're supposed to be able to, with this wording, okay, the sun is above the horizon, to make the drawing yourself. So imagine you would have to go just from this writing to this drawing. So that's the challenge of optics, basically, for most students, is how to translate, and that takes just a bit of practice. Translate these words into this type of drawing. So I need to basically now have a triangle, and I need to find X. So I remember from a triangle, right? I have the opposite side and I want the adjacent. So that's tangent, right? Tangent of 25 degrees is going to be the opposite side, 5 feet, divided by the adjacent side, x. And that's how you're going to find X. And your X is going to be the, right? You just need 2 sig figs. It's going to be 10.7 feet, to which approximately you go to 11 feet. Simple. The challenge here is you're really not given this picture. Once you're given this picture, no problem. But you're not given the picture, so it takes a while to practice, okay? So think about it. Would you be able to do that on your own? Another one, I think you are also not given the picture. This is a picture that I'm providing to you. So a student has built a 15-centimeter long pinhole camera. So what is a pinhole camera? Like your eye, in a sense, is a pinhole camera, okay? Your eye has a lens behind the pupil, but if you ignore that, it works like a pinhole camera, essentially. So pinhole camera is just a box with a very tiny little hole. That's it. So he has a 15-centimeter long pinhole camera. So draw the box with a hole, 15 centimeter. She wants to photograph her 180-centimeter tall friend. So draw the friend outside of the box, far away from the box, and have an image that will be 5 centimeters high. So this is going to be the age I. Okay, we know that this is the age O. How far should the front of the camera be to the friend? So what we need to ask, what we are wanting to calculate, is the D. Okay, so it comes from analogy of triangles, guys, because we know the angle here from trigonometry, the angle here will be equal to the angle there. They have to. They just go in the same, following the same directions, right? So basically, I know these are not right triangles, but you can create a right triangle and say, essentially, you will find that age I is to age O, just like DI is to DO, right? I don't think I have this formula in your list of equations. You can put in your note card, but anyway, it should be logical where it's coming from. So we want to find this one that we essentially is the DO in that formula. And this is essentially the DI in that formula, right? So I invite you to then get that DO then is, or which is the D there, is then just going to be the DI age over HI. So is the 15 centimeters, and then 5 centimeter, 180 centimeters divided by 5 centimeters, okay? So you're going to get careful here because I had centimeter divided by centimeter, no problem. But your final answer basically will be 540 centimeters, which then you can translate into meters as 5.4. Okay, and careful with the units. Just make sure you stick to the same units everywhere, and then there's no problem. If you wanted to give your final answer in centimeters, you could, no problem. All right. The law of reflection. So essentially, the only really useful, more practical use of the law of reflection is the part that says that the angle of incidence is equal to the angle of reflection. Theta R is equal to theta I. What are some of the things, however, I need to highlight to you? Is that these angles need to be measured in respect to a normal imaginary line, normal perpendicular to the surface. So that's number one mistake of students in optics, is that you're going to have a reflected surface. Here it is. What's the first thing you need to do? Draw an imaginary normal or perpendicular line to that surface. Any angle of incidence of reflection, so say is a ray coming in, this is going to be your theta incident, theta I of incidence coming in, and this is going to be your theta R reflected getting out, okay? So these angles need to be measured in respect to the normal line. That's where, so any angle of reflection given to you is going to be this, not this one, not the complementary one. We can call that phi I, and we can call this phi R. These are not the ones that are going to be given to you. It's always in respect to the normal imaginary line. So if you have a surface like this, always immediately draw the normal line because you're going to need. So any angle you're going to measure is in respect to the normal line. Always the angle in respect to the normal line. Big deal. Okay. Study some, right? This some of these examples. There are some nice examples in your book. Basically, you're just following trigonometry. The angles have to remain the same. The angle of incidence is equal to the angle of reflection. So here there's a light bulb. It comes this way and it collides with this mirror, then it reflects. So whatever angle, whatever is this angle theta here, it needs to be the same angle theta here, okay? And by analogy, from geometry, we know it needs to be the same angle here. And it's just asking you, so using triangles just to find relationships. No special formulas, really trigonometry. So reflection, right, is what allows us to see ourselves in the mirror. And in a mirror is, or a very clear, a very nice, steady lake, especially in the winter, that has a very mirror, we say mirror-like surface in the lake. They're called objects that can produce so-called specular reflection, because they are very smooth surfaces. But what if you don't have a smooth surface? You have a highly irregular surface. The law of reflection is still going to happen. But I can't see myself in this puddle here full of oil here on the street. Still, there's reflection happening. You see how it's shining, right? That puddle. You cannot see yourself like perfect, like in a mirror, but does that mean that the law of reflection stopped working? No, it is working. So it means that for every little angle here, the angle of incidence is equal to the angle of reflection. Here, every part, angle incidence equal to the angle of reflection. Here, this is little, draw the imaginary normal line, angle, right? Draw the imaginary normal line right here, the imaginary normal line, angle of incidence, angle of reflection. It's just that the surface is irregular. So what happens is that reflected ray is going to be going all crazy directions. It's not all going to focus and form a nice image in your eye. So that's called diffuse reflection. The law of reflection is still true. The angle of incidence is still equal to the angle of reflection. Those two angles are still the same. It's just that it's happening in different tilts of the surface. And they are not all sorry, combining to go to your eye, and you don't see a nice specular, so-called specular reflection. All right, I don't think I have any problems for you about plane mirrors. You're just going to look, your book has examples. So your book actually uses the letter S for what we called previously DO, and the letter S prime for what we called previously DI. So plane mirrors, like the ones we see ourselves use every day. So here's an object, could be a person, and here's the plane mirror right here. And so following the law of reflection, light reflected on your face is going to go to the mirror and is going to reflect off the mirror with the same angle that it came in respect to the normal line, always in respect to the normal line. What kind of image you're going to see? So with our so the image you're going to see is the image of your face across the mirror, and that image is going to have the same, that image is going to have the same proportion, the same size. So it means that age O is equal to age I, and DO is equal to DI when you're using a plane mirror, okay? So the image is not going to be deformed, it's not going to be distorted because this is a plane mirror. So a good plane mirror, right? So there's no curving and all. DO is going to be DI, meaning the distance of yourself to the mirror is going to be same as the distance of your image to the mirror. And the distance and your size is going to be the same size as the image if you have plane mirrors. So what happens is so this object's not yourself, it's really the eyes you observing. So this could be a bottle of medicine that you're looking in the cabin in the mirror. So our eyes do not understand rays of light curving. Our brain doesn't understand rays of light that curve. Our brain only understands rays of light that come straight. So here's the bottle, right? Here's the bottle. And we know that the light from the bottle came in, reflected and bent, and then came to your eye. That's the law of reflection. That's true. But our eyes will not, our brain doesn't understand rays of light that bend. Our brains only understand rays of light that come straight. So for our brains, that ray is coming from the virtual image that is in the back of the mirror. So what is a virtual image? It's an image formed by not by real rays of light. So it's a, let's call it here in simple terms, a fake image. It's not formed by real rays of light. So no rays of light are going inside the mirror. Nothing is going inside the mirror. Everything's happening on the surface of the mirror and being reflected. So nothing is really entering the mirror. So when you see these rays being drawn, the so-called virtual rays of light, we call them virtual rays of light, okay? You're always going to use dashed lines, virtual rays of light. Always use dashed lines to indicate virtual rays of light. So they're fake, they're not real going inside. But it is important to understand images in general by optical instruments, everything, because our detectors will not always understand, including our brain detector, our eye and our brain, bending of rays of light. So rays are coming straight from behind as if there was something behind. And that's a virtual image. That's the main thing I want to say here. So there are some examples for you to take a look, but it's very simple. Again, you're going to use, this is a nice one. So how tall must be a mirror so that you can fully see yourself, okay? So you know your eye is looking at your feet. So whatever is this angle here is going to be the same angle here, right? And you can use that to figure out this height, that height, etc. And your eye is going to look at the top of your head. So again, you split this in the middle and say the angle here is equal to the angle there, and the little triangle at the top from the eye to the top of the head. and it will help you figure out what is the size of this full mirror. So nice little exercise in example in your book, follow it to understand, or do it on your own and just check the final answer. Okay. All right, let's talk about the phenomenon of refraction now. So what is refraction? We already discussed a little bit about it, right? Light entering, or any wave, light enters a new medium, right? So now it enters a new medium. So it's not just reflected off a new medium, it's entering. So what happens, V and lambda change. Okay, and not just V, but the whole speed, like the direction of the propagation will change. The direction of the propagation will change when it enters the new medium. So the most important law for refraction is this, is called Snell's law. It's called Snell's law. And it says that N1, what is N1? In the index of refraction, remember we said it's the speed of light in vacuum divided by the speed of the light in that medium 1. And then sine of theta 1 equal to N2, speed of light in vacuum divided by the speed of light in the medium 2, sine of theta 2. That's what it is. And what is important here is how to measure these angles. Again, in respect to the imaginary normal line. Number one mistake of students in any test, etc. So you're going to have your surface and you're about to enter from medium 1 to medium 2. Always draw the imaginary normal line. Always draw the imaginary normal line. Always draw the imaginary normal perpendicular to the surface. Then there's a ray coming in, okay? And then it's going to go through, and it's going to go through. So here's an angle. We can call that theta incident or theta in medium 1. And then once it moves through, E is going to have a new angle theta 2 because it will shift directions. My drawing perhaps not so clear, but here you hopefully you see how theta 1 is different from theta 2. How there was a break in the direction, how the direction changed when you went from medium 1 to medium 2. The direction of propagation of the waves will change because of this, the whole speed will change. It's like having a whole army of soldiers walking in concrete, and all of a sudden the whole army of soldiers start walking in a muddy field, a muddy path. I promise to you the lines of soldiers marching will bend and will do the phenomenon of refraction as well. So it's natural that changing direction will naturally happen just because the speed got different. You never need to like memorize this whole table. I would give to you for different materials, but vacuum, we're going to say is 1, and air, okay? We're going to use in vacuum and air, we're going to use the n equal to 1. You don't need to worry about that other one. Water. Water is 1.33. We're going to use that a lot, okay? And it's good to know that glass is around 1.5. There are different types of glass, but it's good to know like the hierarchy of things, okay? Diamond's really large, index of refraction. So a large index of refraction, meaning that in this formula here, N1 sine of theta 1 equal to N2 sine of theta 2, right? So if I go to a large index of refraction, if I go from a small one to a large one, it means that theta will be smaller. The angle will get smaller so that I can balance these equations, right? So if I'm going, for instance, from vacuum or air to diamond, so it's a very large N2, the angle will be very small, much smaller than theta 1, right? To balance the equation. All right. This is an awesome problem, and you should study that very carefully. In your book is one of the examples. Study that. You are now using the law of refraction here, okay? So as you can see, first the ray of light just went in, okay? So that's the problem. Gave you this beam of light and it gave you this angle. This angle is not necessarily what you need. So you need to then make the drawing very carefully and analyze everything that was given to you. So you need to, something was important was happening here right at the surface here. So you draw the normal line. That's the first thing to do. And you know then, therefore, that this is the angle theta 1 that goes in the law of Snell's law. And right. And then and this is going to be, this whole thing is the angle theta 2 that goes in Snell's law. So these are the angles that go in Snell's law, theta 1 and theta 2. You are given just 22.6, but that's not theta 2. So there's lots of things to think about. Right? Not all is just the value that was given to you is immediately the value you're going to plug in the equation. You got to make the drawing carefully and analyze triangles here. There's more trigonometry, yes, and you know how to do it and you can do it. By the way, you can do this with nieces and nephews or kids if you have already at home to show the magic of, well, reality physics and refraction, right? The rays bend so much in change direction when they enter the water, right? That actually the arrow at the end, when it comes out on the other side of the glass, looks like to us that it flipped direction left to right. Another very important phenomenon related to reflection is related to all reflection, refraction, is called TIR. Total internal reflection. This is very important. So as you see from the pictures from Snell's law, or from the formula of Snell's law, right? N1 sine of theta 1 is going to be equal to N2 sine of theta 2. There's going to be a point where maybe one of this sine of theta gets to 90 degrees, right? So imagine here, there's the progression, right? Light, we've learned here, so what is all these little arrows happening here? We've learned that every time light enters a new medium, or here's light from water, let's assume it's water, and going to air, okay? So it needs to be an example like this, from water to air. I'll tell you why soon. You start in water, and so every time light then meets the boundary between the two different medium, part of it will be reflected back. That's where you see this thin arrow, and part of it will go through. Part of it will be transmitted or refracted. And we measure that angle of refraction here from a normal line. This would be the angle of refraction here. In another case, this would be now the angle of refraction. It gets to a point where the angle of refraction is going to get so big that it's going to get to 90 degrees. That's what we have here, the 90 degrees. It doesn't make any sense for a refraction to be greater than 90, because if it's greater than 90, means it goes inside again. So it means it didn't refract, it didn't go through the other medium. It wasn't successful transmitting to the other medium. So 90 is the maximum we're going to get. And this is the critical moment. When the angle starts is 90, we get this critical angle here, we call. So any angle equal or bigger than this is going to, light cannot refract anymore. Light cannot escape anymore. Light's not going to escape. And so total internal reflection is going to happen for theta greater or equal to theta c. So we want an angle greater or equal to theta c. Theta c is measured right here in respect to the normal line, this critical angle. Okay, let me see if I have another little slide. No. So, so when are we going to have this total internal reflection happening? Only when N1 is going to be greater than N2. So we always need to be going from water to air, from diamond to water, from glass to water, or from glass to air. So I need to start somewhere where the speed of propagation is low, where the N is big, okay? Because if this N is big, this N isn't going to be small, sort of small. And then if this N2 is small, right? It means that theta this theta here can get to its maximum value, 90 degrees. So you're only going to make this sine of theta, one of the sine of thetas here, to turn to get to this maximum value, which is 90 degrees, when you have a very small n2 here, so that you can maximize this other side of the equation, right? So what are the conditions for total internal reflection? It's only going to happen if you start in a medium that has a greater index of refraction than where you're going to. So this is an important condition, okay? And it's only going to happen when theta is greater or equal than theta critical. And let's then keep writing this equation here. Oh my goodness, let me see if I can get a better slide where I write more here. Oh, this is the example. Well, let me write over here then. So N1 sine of theta 1 will be equal to N2. And now when we get to, so this theta 1 will be the theta critical when this is a sine of 90 degrees. So the sine of theta critical is then going to be sine of 90 degrees, we know is 1. So it will be N2 divided by N1. Or in other words, theta critical is the inverse sine function of N2 divided by N1. We know that sine function can never be greater than 1, right? So that's why N1 needs to be bigger than N2, right? Only if, again, N1 is bigger than N2, right? You cannot try to put in your calculator sine of 1.5. Right? You try to get the angle you want because we know the maximum value for a sine function is 1. So you can already see how this formula would never work if N2 is greater than N1. So that's the condition for total internal reflection. Anyway, so this is the theta critical. So this is the theta critical. So the angle that the light is then coming in here from the source to the boundary, this is the theta critical. The angle needs to be greater or equal to the theta critical, and then we are always going to have total internal reflection. So let me show you a movie of total internal reflection for you to get a better sense of what is in there. This thing is on top of my... Let me just see if I can move the whole thing. Okay, let's watch this little movie here. So refraction is going to happen when light enters, when light makes a transition between any medium. Here we have an acrylic, a lens made of acrylic, and I want to observe now light. Yes, it entered from air to acrylic, but we're going to ignore that. We're going to observe just this boundary here, from the acrylic to the air back again, from the acrylic to the air back again. So you're seeing how there is a beam of light inside the acrylic and there is a refracted one out back to the air, okay? So the angle in the air, we're going to be always bigger than the acrylic. So this is a situation where total internal reflection can happen because the index of refraction in acrylic is around 1.4, 1.5. Air is 1. So we're going from a bigger index of refraction to a smaller one. So total internal reflection can happen right here, this boundary. Not before, not in any other boundary, this boundary here, going from acrylic to the air, going from a bigger index of refraction to a smaller one, going from a small speed of propagation to a larger one. So because the index of refraction of air is less than in acrylic, the angle, you see the angle with respect to the normal line, do you see the normal line? That angle is bigger than the angle that we had before, okay? Okay, so you're seeing here the refracted ray out in air. Now, it was hard to see this before, but now you start to see it more clearly. It was always there. It was just that it's hard to see. But as I said to you, any ray of light, when it meets a boundary, when it gets to a boundary, part of it is always going to be reflected back. And now you can see how this is the one that is reflected back. It's reflecting back using the law of reflection. But part of it will be transmitted, okay? So this is the reflected ray, is reflecting, and part of it is transmitted. So we can see, because the angle here in air of refraction is so much bigger than the angle in the acrylic, which you would measure from this to the normal line, and here from this refracted beam to the normal line. You see how this angle is so much bigger than that other angle was? So it means I'm going to reach 90 degrees here much faster than I've reached 90 degrees right there. So we're going to get to total internal reflection very soon. Okay. So that means that the only beam of light we're going to have is the reflected beam of light, which you see start to get stronger here. I still have the transmitted or reflected one. By the way, is creating a rainbow here too. Yeah. Okay, there you go. We got to the critical angle. This is the critical angle for acrylic. And now there's no more refracted ray of light. There's nothing. And he keeps increasing here the angle, and there's nothing else goes through. Is all reflected, all reflected. You see, this is a limit of nature. It's a limit of nature that for each material, there's an angle where no light will go through, will stay trapped inside the material. It's a limit of nature. Very cool. Hopefully you understood the this idea. So, and what are some applications of this in fiber optics? Fiber optics is carrying information. You don't want the information to lose intensity or etc. So you want the information to stay trapped and perfectly reflect through the walls of the fiber optics and stay trapped and never go away. So fiber optics has several claddings or layers around them, around the core, so that these are then substances with higher and higher index of refraction, so that even if a ray of light escaped, then we'll have the chance again to bend back and go back to the core. All right, let's apply now our formulas in equations. So let's in problems. An underwater diver sees, so again, this is a case where I'm giving you the picture, but you're not given the picture when you have this problem. So you have to, again, the challenge of optics problems, you got to read the problem and make the drawing. You really have to make the drawing. And the drawing here is given to you, but it's not going to be given in your book. So watch out. That's what I want you to practice now. So the underwater diver sees the sun 50 degrees above the horizontal. Okay, so how are we going to, the diver is here, right? And he sees the sun 50 degrees above the horizontal. So that's what he sees. So you got to draw here into the boundary between water and air. That's where he sees 50 degrees. Okay, now we know that the light from the sun here will come here, it's from air, and then will refract and enters water. So this angle in air will be very different from the angle in water, right? And we use Snell's law. So it will be here, it will be N air, and sine of theta air will be equal to, let's call this medium 1, let's call this medium 2, it will be equal to N water and sine of theta water. Okay. And then notice that 50 degrees is, you should draw 50 degrees above the horizon for the diver, the horizon of the diver, that's 50 degrees. That's not theta water. Theta water is made with the normal line. It's made with the imaginary normal line here. Draw on the normal line to the surface. The surface is the boundary air, water. Gotta always have to draw the normal line. Okay, so how high is the sun above the horizon to a fisherman in a boat? So now I want to know, like, this angle here. So basically, according to the picture, according to the writing there, I should understand that what I want to know is find this angle theta. This is what I want to know. So the fisherman in the boat will see the sun straight line like that, right? No refraction. And I want to know theta for the fisherman. So how does this theta that the fisherman sees relates to theta air? So, right, we know theta plus theta air, well, theta plus theta air will be 90 degrees, will be 90 degrees, will be the 90 degrees over here, right? So I'm going to say that, so theta will be 90 degrees minus theta air. So my job here is to find theta air using Snell's law and then do the rest. Okay, I was given this 50 degrees and I will use it, right? Because I know I just built a right triangle over here. So if I draw it here in blue, I have a right triangle, right? I have a right triangle. This side is 90 degrees, this is 50, and this is theta water. So theta water needs to be 40 degrees, right? So that helps me calculate things. So this I know is 40 degrees. Okay, great. N of water, I will look at a table, but you should also remember 1.33 is a good one, or write in an index card. N air is 1, and then I can find sine of theta air, okay? So you're going to find that sine of theta air, sorry, you take the inverse sine, so you got to practice that. We want two sig figs at the end, so we'll keep a few extra one. It will be 58.8 degrees, okay? So very good. So now I gotta go and plug that in here. So the actual theta that I want will be the 90 degrees minus the 58.8 degrees. So we get our answer, the 33. I know your book says this would be 0.2, right, for us. Because your book rounded more than we did. There you go. Okay, and you didn't need to give that extra digit, actually. 31 is good. Okay, all right, moving on. A 4, again, you're not giving the picture, a 4-meter wide swimming pool. Okay, so that's the width, makes sense. Imagine you have to do the drawing on your own. Is filled to the top. The bottom of the pool becomes completely shaded in the afternoon when the sun is 20 degrees above the horizon. So above the horizon in respect to the air. And then that completely shades the bottom of the pool. That's how you would make that drawing. Look at that. How deep is the pool? So we want to know this D here. Look at that. All these drawings you have to do on your own. Okay, so I'm building a triangle over here, right? So you essentially want to find lots of triangles in these problems, right? And use Snell's law. So I know here that the tangent of that theta water is going to be the opposite side, 4 divided by D, right? So if I want to know D, D is then 4 divided by tangent of the water, the theta of the water. So I got to find this angle of the water over here. So how am I going to find that? I'm going to use Snell's law. I'm going to say that N air and then sine of the angle in air, that's 20 degrees, will be, that's not 20 degrees. Oh, professor, you made a mistake. What is the angles we have to put in our formulas? Always in respect to the normal line. So you got to put the 70, yeah. And then what is N2? N of the water, 1.33, and then sine of the theta of the water, which is measured in respect to the normal line, will give me exactly what I want here. Perfect, no problem. Okay, by the way, sine of theta air is 1. So you solve for the theta water, and you guys will get 40, let's see, 45 degrees. That's what you're going to get, okay? And then plug that in here, and you're going to get that D is going to be your 4 meters. Yeah, so challenge is reading and being able to make the drawing on your own. That's the challenge, okay? Because the math is not really hard. How do you get there? Practicing. Array of light, study the example problems in the book and then solve more, and this is helping and you get your life easier as you go on. Array of light traveling through air encounters a 1.2 centimeter thick sheet of glass at a 35-degree angle of incidence. Okay, so this is the glass, the slab of glass. It has this thickness of 1.2 centimeters. Picture was not given. And this is the angle of incidence. It says is 35 degrees. And because it didn't say in respect to this, in respect to that, if it says angle of incidence, we know it's then the definition from in respect to the normal line that was drawn here, okay? Okay, so how far does the light travel in the glass before emerging on the other side? It wants to know actually R in this. This is not a very nice question here because I have solved problems where you wanted to know this D here. So that question sometimes is not so clear to me. Does he want R? Does he want D? So this problem wants R here. That's what he wants. And this is the picture. I would try in a test to give more hints for you to make this drawing as best as possible. You certainly know what we're talking about. All right, so to find R, we are again going to build this little triangle over here. At the end of the day, we want R. So we build this little triangle here, and we say that tangent, no, this time we don't want tangent. We want what? We want cosine, right? Cosine of that theta on the glass is going to be the hypotenuse, is going to be the adjacent side, 1.2 centimeters, divided by the hypotenuse r. So if I want to r is 1.2 centimeters divided by the cosine of that theta g. Okay, so I need this angle theta g, and it's an angle with the normal line, right? It's making this angle with the normal line here. So that angle and this angle are related using Snell's law. So this is air here, 1 for air, right? Theta and 1 is air. Sine of 35 degrees here will be N2. That's the glass. And typically your book wants to say 1.5 for glass. Don't worry to memorize. I would give to you 1.5 here. And you find that that's your theta G. So once you found this theta G here, you go plug it in there. And then you get your expression for R, which will be 1.3 centimeters. Okay, that's the game. So many of the problems are just like that. Problem with the fiber optics probably involves the critical angle and total internal reflection. What we know about total internal reflection? Well, I wrote that. This is from your list of equation, that the sine of the critical angle will be N2 over N1, meaning the medium where you're entering and the medium that you're leaving. Okay, so here, like the diver on the water, say this is water, and say this is air. So this is the right total internal reflection could happen here. This is theta greater than theta critical, let's say, or equal. So theta, so this is the medium that you're trying to enter, and this is the medium that you're trying to leave. When I wrote this, to me it was very clear, but now I realize it might not be so clear for you guys. So this is N2 and this would be N1. N1 is the medium that you're trying to leave, but you're trapped and fall back, but you're trying to leave. And N2 is the medium you're trying to enter. That's what it means in entering and leaving. Hopefully it's trying to make things easier for you, may not. All right. So the glass core of an optical fiber has an index of refraction 1.6. The index of refraction of the cladding, so around it, so this is 1.48, in the middle is 1.6. What is the maximum angle that light can make with the wall of the core if it is to remain inside the fiber? So again, so what is going to be the medium you're trying to leave, or you're just attempting to leave, is the core, so that is the 1.6. And what is the medium you're trying to enter, but not successfully? 1.48. Okay, so that's what you do here in this problem. It would be just the inverse sine function. So what is the maximum angle, mean the critical angle the light can make with that? Oh, hold on a second. So you want to know the critical angle. I mean, so it's asking the maximum angle, okay? So you know the critical angle is a lower limit, and any angle bigger than that will satisfy total internal reflection. So when it asks for the maximum angle, there's no maximum for total reflection need to be happening. What there is a minimum. It needs to be at least the critical. So therefore, by the problem requiring a maximum angle means that it wasn't asking for theta critical. It really was asking for this phi, because I know theta critical is a minimum level, minimum estimate, a minimum limit, and it can be bigger than the value of the theta critical, and it's going to work. So he wants to do phi because, right? Because as theta critical increases, phi will decrease. So he wants to know the bigger phi, and the biggest phi possible will be when you are at the theta critical. So he really wants to find the theta critical. So that's sine to the minus 1 of 1.48 divided by 1.6. You get that theta critical then is going to be here 67.7 degrees. And if you want to know phi, you know phi is then 90 degrees minus the theta critical, and then we'll give you the 22.3 degrees, okay? And so that's the maximum phi, because then that's when theta critical is the theta is minimum, which is the critical. Think about it. That's what this problem is asking. That's what you get in your book. All right, this one, I made a lot of pictures here to break it down, but that's what this type of problems require. This is a problem level 2, so it's not supposed to be super hard. So what is the angle of the exit angle from the glass prism in this figure? So this is the picture given to you. I wrote those little angles, but this you're given this sort of purple ray coming in, bending, and getting out. Okay, so we want to know this angle theta over here, okay? And you got to do this in steps. The first thing to do, well, it gave you, the first thing to do, because this was coming along a straight line here, you draw a normal line perpendicular to the surface. Draw a normal line perpendicular to all surfaces, right? This normal line here and this normal line here, draw them. You're going to need them. You need to, from analogy from geometry, we know that if we have a straight line and crossing two parallel lines, right? Whatever's the angle that this makes, the sort of the internal angles will be the same. So if this is 45 given the prism, means this will have to be 45 as well. Guess what? This is 90 degrees, the normal line here, dashed red. So this will have to be 45 too, and this is what you're going to use because that goes in Snell's law in respect to the normal line. So the first step is to find theta 1, because now light will bend as it enters the prism. It goes from air to the glass prism here. It says it's glass. You can use n equal to 1.5. Okay, find theta 1. And you use Snell's law to find theta 1, okay? So we've done this a few times. So now I'm just going to tell you the value of theta 1 is going to be 28.13 degrees. So you got to find it. All right. Now that I found theta 1, I know the same ray of light will then do the next, Snell's law needs to be used now with this next boundary here. But now I would need to use theta 2 here. I'll need to do n of glass, right? N of glass, and then sine of that theta 2, and that will be equal to n of air, then sine of that theta that I want there. So that's how I'm going to find theta. So I need to figure out what the heck is this theta 2. I found theta 1. Theta 2 is not equal to theta 1. So to try to make this more clear, I zoomed in on what's happening right there. We create a new triangle here. There's a new triangle here. Identifies not a right triangle, but look how we are creating a new triangle over here. Do I need to do this? Yes, you need to do this. There's a new triangle. What do we know? That the sum of all the angles inside of a triangle is 180. So theta 1 plus theta 2 plus 135 equal to 180. Okay, we know that. Okay, the problem is finding 135 here. So how would you do that problem? Well, hopefully you figure it out, but boy, so I zoomed in now here a little bit more. If you, again, if you're confused with this that I did, then boy, forget about me and do on your own. I just was trying to help you. So I'm zooming in just when what is happening here, the 135 there. Okay, we know the top of the prism. This is the prism is 45 degrees, 90 degrees here, and so it's 45 at the top as well. And this is the, so you can, you're just gonna search for lots of little triangles here, okay? If the top of the prism is 45 and you make 90 degrees with the normal line here, and this angle is theta 1, okay, then you can create this red, yellow sort of triangle over here and find that this angle then has to be 45 as well, right here, right here. You know the rest is 90, so 45 plus 90, 135. That's how you get 135 there. Anyway, so now then you can find theta 2 then. Theta 2 is then going to be 16.87 degrees. Always keep extra digits, and now you plug that into Snell's law here and find the final theta, which will be 26 degrees. So solve this problem step by step. Your book had an example of that type of problem. Again, you need to just be careful with the triangles, create triangles, and always geometry. All right, so the law of refraction, or Snell's law, is because light bends in direction, right? What happens when it enters a different medium is why we see things apparently as broken, right? When we go from one medium to the other, right? So it makes the objects look odd, and the objects will always appear to be closer than they really are. Law of refraction makes objects appear to be closer than they really are. So Indians, Native Americans knew that when they were fishing, they needed, the fish was always going to look at a shallower the depth than they truly were. Refraction also is the reason why you have mirages in the desert and in the asphalt on a very hot day. So refraction, what is it? Is that bend or change in direction of the rays of light because change of condition of the medium. And so in a very hot day, so what happens is the temperature is a lot higher close to the surface. And so it's as if the ray of light is, as the temperature is increasing, as you're getting closer to the ground, it's as if you're changing the medium all the time. And the rays of light, therefore, they bend, keep bending. And they practically curve to get, from the object to you. But our brain does not understand curved rays. Our brain thinks the light is coming straight along a straight line. So we see at the mirage underneath, because we think the light is coming straight. So atmospheric refraction, when you see the ray, sun kind of, right, bent, doesn't look straight. The other topics, I'm not going to refer to all of them right now. Guys, this is where I'm going to get with these online classes, these online 3 online videos I sent to you now. And when we come back next class, we talk about formation of images with mirrors and lenses. And that's what your lab is all about. We briefly talk about the human eye, and these are the topics for your test next week. All right, bring questions to class.